Octavio.
¿Continúo de inmediato?
Sí, claro.
Sí, sí.
Muy bien. Bueno, entonces, buenos días nuevamente. Sean bienvenidos a la primera conferencia plenaria del Foreign International Conference on Mathematical Modeling. Es un gusto presentar al doctor Zenén Barro Ameneiro, quien aceptó nuestra invitación para participar como ponente plenario. El doctor Zenén Barro Ameneiro es licenciado en Física y doctor premio extraordinario por la Universidad de Santiago de Compostela, USC, catedrático del área de Ciencias de la Computación e Inteligencia Artificial. Ha sido profesor de Informática e Inteligencia Artificial desde 1995. Fue director del Departamento de Electrónica e Informática de la USC entre 1993 y 2002. También ocupó el cargo de rector de la Universidad de Santiago de Compostela, asumiendo el cargo el 17 de junio de 2002 y siendo reemplazado por Juan Cázares Long en 2010. También fue vicepresidente de la Conferencia de Rectores de Universidades Españolas desde mayo de 2008 a junio de 2010. Zenén Barro es investigador adscrito al CITIUS, Centro Singular de Investigación en Tecnologías de la Información, desde el que dirige el Grupo de Investigación de Sistemas Inteligentes. Actualmente es investigador colaborador e investigador responsable de numerosos proyectos de investigación y contratos internacionales en la Unión Europea, estatales y nacionales. Desde mayo de 2008 es el presidente de Red Media, que promueve la innovación y el emprendimiento responsables, y de la que forman parte 28 universidades iberoamericanas, Universia y Banco Santander. Es autor de unos 300 artículos científicos y miembro fundador de CITIUS Technologies, S.A., una spin-off de la USC dedicada al posicionamiento en interiores mediante móviles. Ha realizado estancias de investigación en el Departamento de Informática Médica del Royal Free Hospital de Londres y en la Universidad de Bristol, Reino Unido, y en la Universidad de Maryland y en la Universidad de California en Berkeley, en Estados Unidos. Es académico numerario de la Real Academia Gallega de Ciencias desde 2015. Adelante, doctor.
Y además, perdón, además es amigo de la Universidad Tecnológica de la Mixteca. Con él firmamos un convenio de cooperación y entrañable amigo mío, así que estás en tu casa, Zenén.
Muchas gracias, Modesto. La verdad es que yo iba casi a empezar por ahí, por decir, en fin, la extraordinaria ilusión que me produce ser ponente plenario de esta conferencia, por la importancia de la conferencia, pero sobre todo, tengo que decirlo, y ya en el terreno personal, por ti, Modesto, porque bueno, nos une una estrecha amistad y a mí casi una veneración por ti, ¿no? Y por el trabajo que estás haciendo ahí, porque para mí es de esos milagros lo que has hecho en Suneo y con toda la gente que lógicamente pues te ayuda cada día. Es uno de esos milagros que todavía, y sobre todo en estos tiempos tan difíciles, ¿no? Pues le hace a uno seguir teniendo fe en las personas. Es verdad que no en todas por igual, pero con personas como tú, desde luego uno pues, se levanta contento cada día porque sabe que al menos nuestra sociedad tiene a gente que la va a sostener y la va a llevar adelante. Bueno, a continuación quería preguntaros si la conferencia ha de ser en inglés o no, porque yo había entendido que sí, pero si nadie de los que me escuchan, o dicho de otro modo, en positivo, si todos los que me escuchan hablan español, yo continúo en español, vosotros me diréis.
Pues por unanimidad se dice que sí.
Sí, la mayoría de los espectadores es...
¿Hay algunos que hablan inglés?
No, pero si hay gente que no sepa español, cambio al inglés. O sea, yo la he preparado en inglés, no tengo problema. El asunto es, digamos que...
Parece que algunos de los espectadores sí se hablan inglés.
Bueno, pues entonces la daré en inglés, aunque no será de tanta calidad, desde luego, como en español. Pero bueno. Before I start my talk, I would also like to have a loving memory to Dr. Mario Molina. As all you know, Mario Molina was a Nobel Prize winner, a Mexican Nobel Prize winner, who died yesterday. And as far as I know, he was the only Spanish language Nobel Prize winner in science who was still alive. I'm not sure about this, but I think so.
Doctor, ¿podría compartir su pantalla, por favor?
Sí, claro. Era justo lo que iba a hacer. Muchas gracias. Se ve, ¿verdad?
Sí se ve.
Sí.
Okay, so the title of my talk is Machine Learning in a Society of Devices. I'm not going to talk about mathematical modeling, but anyway, and in fact, I'm going to try to avoid as much equations and mathematics as possible. In artificial intelligence, we use mathematics a lot. But anyway, in this talk, I'm going to try to show you or to explain you some concepts and not mathematics. So let me start just in 1 or 2 minutes to present my research center. I am the director of the CITIUS. The CITIUS is a research center on intelligent technologies of the University of Santiago de Compostela. And there are more than 110 researchers in the center. 32 of us are senior researchers, and most of the rest of these researchers are PhD students. So every year we have between 50 and 70 PhD students in the center. So our research activity focuses on 8 scientific programs, most of them in artificial intelligence and the rest in related or satellite fields of artificial intelligence, or even in some fields that provide physical and computational support to artificial intelligence. 2 in 3 of our papers are published in Q1 journals and 1 in 3 in D1 journals. And every year about 10 doctoral theses are defended. And in the last 4 years, we have raised more than 10 million euros. In fact, close to 4 million euros during the last year in 2019. I'm sorry. And during this period, I'm talking about the 4 last years, we have signed more than 35 contracts with industry. We have a increasing activity in international projects, mainly in European projects. And in fact, I am the coordinator of ETN. ETN is a European training network with a funding of close to 3 million euros. And well, anyway, in addition to publishing top papers, we are very proud of having a great socioeconomic impact through the transfer of the results to our research. I'm just going to give some very, very simple examples, but I think that all of them are quite nice. One is Galleyweather. Galleyweather is a software that we have developed, and this software makes the narration in natural language, in Spanish and Galician, of the weather forecast for each one of the more than 300 city councils in Galicia. In recent years, we have created 2 spin-offs, employing nowadays more than 40 people. So a very, very big number of people, because these 2 spin-offs are very young, less than 5 years old. And we have another one in incubation. And we are now transferring a software system based on deep learning for the detection and tracking of small objects in video images, as small as 4 by 4 pixels in size. And we are in the process of being transferred this software to Indra. Indra, probably some of you know this company. It's a Spanish company, but this is very huge, and it's a company that controls around 60% of the world's air traffic all over the world. And finally, we are very proud that we have recently organized the ECAI 2020, which was the 24th European Conference on Artificial Intelligence. And this was the first time, in fact, in almost half a century that ECAI has been fully digital due to the COVID-19. And the numbers of this conference was have been spectacular. More than 400 papers, and even that just 1 out of 4 has been accepted. More than 500 hours of content over 10 days. More than 5,500 attendees from all over the world. More than 2,000 people are actively involved. I'm talking, the meaning of actively involved means that reviewers, speakers, participants in roundtables, chairpersons, and so on. So thank you for listening me this commercial. And now I am going to talk to you about the topic of my talk. And well, everybody knows that the number of smartphones now exceeds the number of people in the world. And when in 1999, just 21 years ago, Kevin Ashton coined the term the Internet of Things, he hardly could imagine that 20 years later, there would be more than 30 billion IoT devices worldwide. So IoT devices and many other devices such as smartphones, robots, cars, incorporate a growing capacity for sensing, computing, and action. Additionally, most of them are somehow connected to the cloud, and they can gather huge amounts of data from the environment because they are becoming more and more sensorized and connected. So we can use this data, applying machine learning techniques, for improving the capabilities and the performance of these devices. Obviously, such learning will be much more interesting and potentially useful if done collectively rather than individually. But doing that collectively presents significant difficulties such as scalability in terms of storage, communications, and computational costs, problems with privacy preservation, or problems regarding the non-stationarity of data, between many others. I'll talk about some of them later. So in my talk, I will analyze the field of collective machine learning, which is a very recent field of machine learning, but with a rapidly growing interest between the scientific community and even between the companies at large, and absolutely essential for our society of devices and data. So I'm going to talk about some strategies of collective machine learning, the influence of the origin and organization of data, some examples of applications, some from my center, my research center, including, and finally, some of the most relevant open challenges in this field of collective learning. So this is a very short, very well-known, anyway, elegant and even beautiful definition of machine learning from Tom Mitchell. A computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by B improve with experience E. I love this definition. It's very simple, but at the same time, it's a conceptual definition, but practical. And is the definition as practical as in fact is the definition of machine thinking proposed by Alan Turing in his paper entitled Computer, Machinery, and Intelligence, when he asked himself if can machines think. By the way, this paper was published in 1950, so this year is the 70th anniversary of its publication. In general, machine learning was thought and developed on the idea that a single, and I repeat, a single machine could learn from its interaction with the environment. So so that although there were other machines in that environment, the learning was individual. However, the society of data and the society of devices, and I use this name, society of devices, in a double sense, since we have society of devices and our society, the human one, is increasingly conditioned by them. Well, this makes not only useful, but even necessary to incorporate collective machine learning. And let's see a pseudo-formal way the concepts of individual and collective machine learning and some of the most common strategies of collective learning. And just as a disclaimer, due to collective learning is a very new field, just from more or less 2016, so 3, 4, 5 years old at most. So there is probably by this reason, in fact, there is quite a lot of confusion in the use of the terminology associated with this field. Therefore, it is possible, in fact, it is almost sure that in the bibliography you will find different names or even different meanings for some of the words or expressions I am going to use. But in any case, I hope that beyond the names, the concepts are clear. So I'm going to define individual learning. From now on, we will assume that an entity will operate in a world in which it performs a task with a performance measure, P, using a model. I'm talking about a model for solving that task, learned based on experience, the experience of this entity in that world. So this experience can be a data set obtained by the entity in its interaction with the world, for example, a smartphone, or provided by any other entities or data source in that world. Examples of this is this of the smartphone, but for example, a smartphone that is monitoring its users' work, or a weather forecast service using the information provided by a set of weather stations. So the model for solving a task can be dynamic. Most of the times is dynamic, trying to improve its performance from experience a long time. In this way, individual learning of a task will take the form of a function depending on the model and the experience of the entity. In this way, we can improve the model a long time. And the goal, of course, is to reach a performance measure greater than a reference threshold for the desired entity's performance. Some important point. In the following, we will explain what is meant by collective learning and for which machine learning problems it is particularly suited. But before that, it is important not to confuse distributed learning with a kind of collective learning. At least from my point of view, distributed learning divides the effort of individual learning across several devices or systems, whereas collective learning uses multiple entities to learn how to better perform a given task. So I'm going to define collective learning, and suppose we want a set of entities to collectively learn how to solve a task from their experiences. This means to find a method for calculating this general function, so that, as in the individual case, the performance measures will be greater than a specific reference or threshold if T is long enough. Examples of learning the same task based on many experiences is learning to detect steps when walking using the experiences collected by a group of people using their smartphones, or improving say, the detection of obstacles on the road while driving using the data provided by a pool of autonomous cars, self-driving cars. An example, on the contrary, an example of learning different tasks, although being similar one to each other, is to learn the way the owners of smartphones works as an element of biometric identification for unlocking them. I'll talk about this particular example later. So in centralized learning, a set of entities share their experiences with a central system, which will learn from them, from the experiences, and for them, for the entities, the model for solving one specific task or a set of tasks, which means to find a function for obtaining an improving model for solving the task a long time. This function has this shape, and centralized learning for solving a task is generally computed, not always, but generally computed on a client-server architecture, and usually follows the following procedure. In the step one, clients send their data to server, specifically being handled to add privacy and security if that is necessary. I'll talk about this point because it's really important when we talk about collective learning. In step two, the server uses all data to learn a solution for solving the task. In step three, the server sends the solution to clients, and the solution may or may not be adapted to each of them, to each of the clients, according to their specificities. And in the step four, the clients adopts the solution provided by the server and operate with it normally. So the solution, let me explain what a solution is. A solution in this case is a model for solving the task or the tasks. This solution can be learned only once, sporadically, or even regularly if it needs to be updated from time to time. I'll give you an example of a centralized and non-centralized or decentralized solution to a task that affects us directly in these times of pandemic. It will help me to introduce some ideas that I will use later to continue talking about collective machine learning. Nevertheless, it is an example of a centralized solution, although not an example of a collective machine learning, but it's an example for data analytics instead. And the sample is regarding the contact tracing applications or apps. A contact tracing system to fight COVID-19 that most countries have adopted, particularly in Europe, is the decentralized one. In this system, the comparison between infected people and those at risk of having been infected by them is done on smartphones, as everybody knows. On the contrary, in a centralized system, there is a central server that holds the information concerning the interaction between people, although anonymized. In this way, the matching to detect contacts of potential risk of infection is done in the central server. In this case, the health authorities can access to this information, and not only for alerting people with a high risk of having been infected by other person who has tested positive for COVID-19, but also for obtaining information of great epidemiological value. Since the social interaction map would be available, it could be possible to use very valuable information for data analytics and even for machine learning. But this is not possible because in most of the countries, at least, because most of the countries, Spain is a case, I don't know the case in Mexico, but in Spain, we are using the decentralized system. So of course, much more respectful with the privacy of the data, but we lose a lot of information, which is really very, very important from an epidemiological point of view. And this is very important because centralized learning has unquestionable advantages, such as having together all the data for machine learning or for data analytics, but it cannot normally be used when the data sources are distributed or they belong to different owners, being individuals or organizations, it doesn't matter. Owners who cannot share them, and the laws that protect privacy by limiting access to the data, to this data, in particular personal data, are increasingly common. In fact, think about the European Union's General Data Protection Regulation, known by the acronym GDPR. This is an example, but in most of the countries is more or less the same. When there is not, so if there is not a solution, or at least an easy solution to bring the data together, we need other approaches than centralized learning. And that explains why, although collective learning is still in their early stages, I used to say in its infancy really, it is receiving a lot of attention, not only by the scientific community, but also by companies. Let me start to deal with federated learning, which is, from my point of view, is a case very powerful, but it's a case of collective learning. Just quoting some of the pioneers in the field of federated learning. Federated learning is a distributed machine learning approach which enables training on a large corpus of decentralized data residing on devices like mobile phones. So federated learning has been proposed very recently, but at the same time, due to its origin, it is usually identified with machine learning involving multiple devices. And this definition is in fact an example of what I have said before about the great confusion that exists in the use of terms when we talk about learning using multiple devices or multiple data sources. I'm talking about the identification between federated learning as a distributed machine learning approach, which is, from my point of view, wrong. Well, on the other hand, federated learning and collaborative learning are usually considered equivalent, as it happens in this Wikipedia entrance. But again, I think that this is wrong. Well, in fact, due to several reasons. There are other forms of collaboration within collective learning than the federated approach, at least as I am considering it. And moreover, I am sure that in the coming years, there will certainly appear many new contributions in the field of collective learning involving different types of learning, both cooperative, but also competitive. And many of them will be bio-inspired, in fact, and also a variety of different architectures for implementing them. So, we associate federated learning with a set of entities that share the models, not the data, for solving a task that they locally learn based on their experiences for collectively improve them. In general, this process can be seen as the composition of two learning functions, a local one, IL, and a collective one, CL. And let's see that in this way. And let me explain what IL and CL are. IL is the individually learning. Every client, every device, every node in the collective learning is applying this kind of individual learning, trying to improve their models for solving the task. And in the server, we apply another function depending on the models calculated by the nodes or the clients, trying to obtain a global, a general solution for that task, a general model for solving that task, in fact. So the idea is the same, is to learn how to solve a task in the best way possible, but in this case, collectively. So what we try to do is to obtain a measure of performance collectively, which is as close as the measure of performance obtained using a centralized approach. So an approach that uses all the data, which is not possible in most of the applications, in most of the cases when the data are divided in different machines or devices or databases, or they belong to different entities, different people or institutions, as I said. So client-server architectures are particularly suitable for federated learning that works on datasets that share the same set of variables or features. For example, those that would come from a set of weather stations distributed over a territory. The following in this figure is the general procedure for a federated client-server architecture. And let me explain briefly the meaning of the different steps. Step one, end clients and devices or end providers of data learn to solve a task on their data sets, normally from a starting model provided by the server, and which is usually the same for all clients, at least when all of them have to solve the same task. In step two, the local models, I insist, not the data, not the local data, but the local models for solving the task, resulting from the local learning, are sent to the server after specifically handled to add more privacy and security if that is necessary. In step three, the server uses all the local models to learn a better model for solving the task. In step four, the server sends the solution to the clients, to the end clients, the solution, and this solution may or may not be adapted to each of them depending on their specificities and or the task they are responsible for. And in step five, finally, the clients assume the solution provided by the server and operate with it in normal conditions. Normally, this procedure is repeated so that the clients continue to improve their models for solving the task they are responsible for until a stopping criterion is verified, and such as, for example, having achieved a given local or collective performance, for example. So one of the main problems of collective learning, and in particular of federated learning, is how to combine the models that different clients use to solve the task in order to, of course, to learn from them and improve them. Most of the solutions to date use the same model, and in particular, deep learning neural networks. In this case, it is, well, they use it, even in our case, we use in some applications this kind of models, and we use it because it is relatively simple to combine the models learned by the local devices. So because, as probably you know, the DNN, the deep neural networks architectures use in each client, if they are the same, it's quite easy to learn collectively because we just need to deal with the gradients or the weights in order to attain a global or a collective model. So for example, this is a very popular algorithm. I think that it was published in 2016 or 2017, I don't remember. And is very popular because it's very simple, but it's very powerful. It works very well. And in this case, the authors just use the average of the weights of the links between neurons in the deep neural network model. And is in some sense is a generalization of the federated stochastic gradient descent, allowing local nodes to perform to perform more than one batch update on local data and exchanges the updated weights rather than the gradients. In fact, in federated stochastic gradient descent, if all local nodes start from the same initialization, which is possible in most of the cases, averaging the gradients is strictly equivalent to averaging the weights themselves. So it's quite easy to join together all the local models and in order to attain the global model. Let me just say very few words regarding some advantages and disadvantages and pros and cons regarding the federated learning. And in fact, these are in many cases common to collective learning, not just for federated learning approaches. The main advantages are the privacy preservation by design, because we use to learn collectively the models of the local devices instead of the raw data. So it's at the same time more secure because the data models and agents are distributed, and scalability is another advantage, because due to the distribution of the learning process on clients, reducing memory communications and processing time requirements. In fact, in many applications, a strong motivation for using federated learning is to maximally use the computing power at the edge devices of a cloud system, for example, in IoT applications. But this model, well, it's not a model, this type of collective learning approaches, the federated learning, I mean, has some disadvantages too. One is the partial view of the problem due to the use of distributed data sets, possible problems of convergence of the learning process with its performance also, especially when the number of entities or the number of devices is very large. And their experiences are not similar, in fact, which happens most of the times. For example, they present quite different probability distributions in data or unbalanced data sets and so on. Well, there is slow and unstable communications depending on the entities involved in the collective learning process, difficulty in guaranteeing the reliability of data source by malfunctioning of devices, low quality of data sets, either through negligence or even through bad intentions of the managers of these data sets, possibility of attacks which can corrupt one or more local models, which affects collectively the learning performance. Well, and finally, the need for all clients to operate with a common model for task solving, or at least with models easily projected one on each other. I'll talk about this point because it's very important later again. Well, let me give you just a very nice example, a real example of federated learning. application is out of vocabulary words learning using smartphones. Is an I think that this was applied in 2019, so just 1 year ago, and the idea is the following: out of vocabulary words. The idea is to learn out of vocabulary words based on frequently typed words from mobile devices. When I talk about out of vocabulary words, I want to refer to words that are not included in the vocabulary of a user's mobile device, for example. Words missing from the vocabulary cannot be predicted by keyboard suggestion or autocorrection. So this is a clear example where it is not possible to share data because the data comes from different users and is personal, is sensible, so nor is feasible to learn from the individual experience of each user. In this case, because the individual experience of every one of us is very narrow when we use this kind of applications. So during this process, the out of vocabulary generation model in each user smartphone is constantly getting updated, while the training data remains on the device. So there is no problem with the privacy in this case. And this is, as I said, is something which is important when we talk about the federated learning. So as a result, each mobile device ends up with a powerful out of vocabulary generation model using this kind of collective learning process. Well, let me just say something about another way of collective learning, which is the peer-to-peer learning. A peer-to-peer learning allows the learning models of the different entities to be exchanged with each other in order to improve them through the composition, some kind of composition of these learning models. Additionally, each client can use its own data for the collective learning process, even in cases where the data cannot be shared between clients, because it's using its own data, not the data from other clients. Anyway, depending on the learning process, it can be necessary some kind of coordination between peers to properly manage their participation in the collective learning process. And let me give you an example where the cyclical peer-to-peer model, the model of the right, was used to learn how to identify on a smartphone the user's way of walking as a method of unlocking the smartphone as a biometric password, in fact. The data set for local learning comes from the acquisition by a smartphone of its owner walking data. But having only the data of the smartphone owner is not enough, since it is necessary not only to recognize the walk of that person, but also to discriminate it from that of any other person. So this requires learning on data from many other people. However, we assume that the personal data cannot be directly exchanged between the smartphones or sent to a server that could use it to learn all the models for solving the problem. So we could consider anonymizing or encrypting the data so that it can be handled outside the device, outside the smartphone that provides the data. But another possibility is that each smartphone uses its own data to improve the models of the rest of the smartphones and vice versa. So each client uses the received model and its experience to improve its own model. And a direct way of doing this is that the client replaces its own model by the received one, if in case that model is better or has a better performance on its data sets or on the data sets of the smartphone who is dealing with the reshaped model. So let me say something which is important in order to deal with practical applications about the relationships between multiple data sets. We are now interested in talking about different ways in which two data sets, two or more, but I'm going to just analyze the case of two for simplicity, in which two data sets from two different entities are related, although the same reasoning, as I said, can be used to any number of them. So we will consider two different entities, which provides two data sets, so their experiences concerning the same or different identities and associated with the same or different set of features. I mean features are variables that describe the identities. For example, physiological variables in the case of a patient. So when the identities are the same and the features, the set of features are different, we have complementary descriptions of the same identity. So some kind of aligned disposition. When we have different identities, but the same set of features, we have a similar description of different identities, some kind of stacked or in horizontal disposition. And when we have different identities and different sets of features, it means that we have different ways to describe different identities, which in the worst case will not allow some useful learning concerning both identities. This is what is commonly known as mixing pears with apples. But depending on the degree of overlap that may occur between the referred identities and the features that define them, we can find different learning processes applicable to them. So let me analyze these two main forms of relationship between two data sets. In the first case, in the upper case, stacked data sets, each entity provides different samples, but all of them refers to the same features. For example, the data collected by two similar electrocardiographs from electrocardiogram monitoring of two patients, or the data collected by two different wearable devices which have the same set of attributes, since the sensors of these devices are the same or close or very close one to each other. And in the second case, in the middle case, we can think on the medical records of the same patient in different medical centers, for example, which record different physiological variables, as I said before, and other medical results. So in fact, one example of federated learning using a client-server architecture in the medical domain is a very nice project which has just been approved for funding, and the CITIUS, my research center, is involving on it. And this project is designed to learn deep learning algorithms to diagnose COVID-19 and other lung diseases on chest X-rays. The information from patients hospitalized in the different participation hospitals will serve locally to improve a common model for a diagnostic system. So in order to avoid having to share patient data, which is not possible in this kind of applications, we are going to use, in fact, a federated learning approach on deep neural network models. And I'm very sorry because I think that I'm running out of time, and I have a lot of things to say. So I am going to to avoid some parts of my presentation, because in other case it will be impossible to talk to you about the kind of applications and the kind of approaches, solutions we are doing in my research team in the CITIUS. So I think that it is important, at least for us, to share this knowledge and this information with you. So I'm going to avoid this and the next one, if you don't mind. Sorry about that. I am going to talk about collective learning applying in our research center and say something about that. So this the following figure illustrates the collective learning process that we follow in our research team. As I said before, well, one of the problems with collective learning is the problem related with the continuous learning process. In many situations where the data evolves a long time, it is necessary a continuous process, not just to learn once or from time to time, but continuously. And we are dealing with this problem in some very nice applications. I'm going to talk to you about one of them at the end. So, well, this figure illustrates the general model of collective learning we are using, we are dealing with. When, in this case, when the server obtains a new global model, because from time to time, not periodically, because this architecture is works in asynchronous way, but when some specific device and local nodes and client decides to send to the server his local model, the server uses this model in order to improve the global model. And once the server obtains a new global model for solving the task, it sends it to all devices so that they operate with it for solving the task in their operating environment. So another point which is really important is that in our case, we use different models associated with the different devices, with the different smartphones. So we don't need to use the same model, the same, for example, deep neural network, in order to learn to solve a specific task. So,
2 minutos, doctor.
2 minutos.
3 minutos.
So I am in a hurry, because in 3 minutes I can say almost nothing, but I'll try to do that. So some very important characteristics of our collective learning research is that we use different learning models associated with the different devices. We use an asynchronous way of learning, a continuous way of learning, which is very important. And also, at the same time, we deal with something which is important in most of the application, which is the concept drift problem. When we have situations where well, for example, most machine learning algorithms work under the assumption that data comes from a static distribution, so independent and identically distributed data. But this is an assumption which is not true in many real-world applications. So we have developed some approaches, nice approaches, in order to deal with this problem, with the concept drift problem. And in that cases, the local devices, the local clients, are able to adapt themselves to the data along the time. So always their local models for solving the task, but what is much more important, the global learner model for solving the task is able to operate in the environment. And just for finish, this is an example of a real application we are using and we have developed, in fact, in my research center, in my team. So it's a practical application we are now exploring for obtaining real experience about collective learning. It's a kind of experiment, a permanent experiment. And this application is for human activity recognition. We use smartphones for recognizing activities like walking, standing, going upstairs, going downstairs, and others. And in our application, we use a data set that contains data from 10 different users performing 7 different activities with the smartphone placed in 5 different locations of the body. And by the way, and just to have a baseline, this is the best accuracy we are able to obtain applying some of the most popular classification methods, for example, CNNs, but considering all the data together. So using the whole view of the problem, this is the result, the performance of the different approaches. And this is a reference for us, because what we try to do is to go as close as possible in a collective learning approach to this, to the best of this performance. And in fact, we obtain very, very good results applying our collective learning approach, as you can see in this case. For example, here, the different colors are different users. As I told to you, we have 10 volunteers giving us data about this task. And in an ideal situation, we obtain a very good results, close to 0.9, as best as the best of the global view, the problem solved with a centralized approach, which is the best we can do, of course. And even in the case where we add noise, for example, noise to noise addition in 4 cases, due to the collective learning and not the individual learning approach, we obtain very good performance, very close to the performance in the ideal situation. And even if we consider the concept drift problem, so the data is changing, even in some cases very fast, due to the collective learning properties, we obtain again very good results, very good values for performance. And this is the last one, I promise. And this is just to share with you some of the collective learning challenges that are open, because this is there are even more than this, but just these, I don't know, 9, 10 challenges is something very, very difficult to deal with, because probably because this is a very recent, very young field. So there are a lot of problems that we need to solve before to have collective learning as a commodity. But for sure, this will be the future, because as I said at the beginning, I want to finish with the same phrase: we live in a society of devices. And well, unfortunately, we ran out of time. So, and in fact, I have consumed more than I had intended, and even more time that I have been given. Sorry about that. I'm very sorry. And I hope this is not a problem. And if you have any questions, and we have some minutes, I can try to answer them. But in any case, don't worry about that, because I will be happy to answer any questions or to receive any comments or proposals by email or even on a video call. So thank you very much for inviting me, and well, I finished.
Muchas gracias, doctor. Pasamos a la sesión de preguntas. Si gusta, doctora Verónica.
Sí, muchas gracias. Bueno, tenemos algunas preguntas. La primera es del doctor Tomás Pérez. Dice, dentro de cada modelo se consideran herramientas de ciencia de datos, es decir, se realizan búsquedas en las bases de datos.
No, en general no. Eso forma parte de lo que se llama el ciclo de vida de los procesos de aprendizaje colectivo. Es decir, yo aquí he dado la visión de lo que es la parte central, el core de las aproximaciones de aprendizaje colectivo, o en sociedades de dispositivos o con múltiples fuentes de datos, y por tanto me he centrado en cómo aprender conjuntamente a partir de visiones locales una forma de resolver una tarea global y que pueda después ser compartida a los nodos locales. Pero desde luego, como ya he dicho, eso es la parte central. Hay mucha parte que rodea todo esto que hay que tratar en un problema real y aplicado. Y, por ejemplo, tiene que ver con cómo accedemos a los datos. Si, por ejemplo, los datos son aportados por dispositivos, un smartphone, por ejemplo, y son aportados directamente a la nube, pues esa es una opción. Pero hay casos donde accedemos a bases de datos, efectivamente, como en el ejemplo del proyecto de COVID, usando bases de datos de pacientes infectados y no infectados de distintos hospitales de España. Ahí no estamos accediendo a dispositivos que directamente envían sus datos a la nube, sino que se accede a bases de datos que pueden tener pues, estructuras organizativas distintas, algo que hay que contemplar. Pero eso podemos decir que forma parte o de técnicas o de aproximaciones de preprocesado, de tratamiento de datos, o de acceso a datos, de organización de datos, de almacenamiento, de recuperación, pero digamos son satélite de lo que propiamente es el aprendizaje colectivo.
Muy bien, pues tal vez tengamos tiempo para una pregunta muy breve. Esta es por parte de Carlos Flores Cabanillas. Dice, mi pregunta es acerca de cuáles serían los mejores algoritmos para Machine Learning.
Bueno, los mejores algoritmos depende del problema. Y una cosa es el Machine Learning individual y otra cosa es el Machine Learning colectivo. Si quiere, le aconsejo un trabajo que publicamos en el año 2014 y que tiene ya más de 2.000 citas en Google Scholar, que precisamente analiza en torno a unos 100 modelos distintos de clasificadores, precisamente para ver sobre qué tipos de problemas funcionan mejor según qué tipo de clasificador. Al final se ve, y por eso yo creo que este artículo es tan citado, nosotros demostramos que hay, con unos pocos, se puede cubrir prácticamente el rango de posibles aplicaciones sin problema. ¿Qué significa eso? Desde un punto de vista práctico, y si me permiten decirlo, bueno, que se han publicado miles y miles y miles de variantes y de clasificadores que son inútiles desde un punto de vista práctico. Pero una cosa es eso y otra cosa es lo que es mejor para el aprendizaje colectivo. Cuando hay que aprender colectivamente, los modelos que se aprenden localmente tienen que ser fácilmente, o al menos tiene que ser posible, fundirlos entre sí. Es decir, que lo que aporta uno a través de su aprendizaje local y lo que aporta otro, después se puedan convertir en un modelo único general, global, para que todos ellos operen con él mientras no se actualice de nuevo. Y ahí sí que tenemos serias limitaciones. Por eso casi todo el mundo usa redes neuronales y particularmente usa las Deep Neural Networks, porque son muy potentes desde el punto de vista del aprendizaje, pero además, si la arquitectura es la misma, simplemente con un promediado de datos o tratando con los gradientes, ya podemos fundir los modelos locales en uno global y entonces es fácil hacer ese proceso.
Muchísimas gracias. Pues no tenemos tiempo para más preguntas, pero agradecemos enormemente al doctor Senen por su ponencia. Bueno, le hacemos entrega de una constancia por su excelente charla de manera virtual. Físicamente en estos momentos sería imposible, pero se la haremos llegar de manera electrónica. Y bueno, pues quisiera dar gracias a todos los participantes. Los invitamos a continuar participando en el Congreso, en las distintas charlas del Congreso. En la página del evento están todos los links para que se unan a las pláticas que continúan en las sesiones paralelas y más tarde en las plenarias. Muchísimas gracias a todos y bueno, pues con esto concluimos nuestra primera plenaria de este Fourth International Conference on Mathematical Modeling.
Y gracias, Ana. Gracias, muchas gracias.
Y me dejas solo
Gracias
30
a ustedes.
segundos. Desearos lo mejor y mucha salud. Y a ti, querido amigo, querido rector Seara, querido Modesto, ya sabes lo que te quiero, mis mejores deseos y lo que te admiro. Para ti y para tu familia. Cuídate mucho y cuida de ellos.